All right, so now the audio is working. See, I thought I had the sense I should check the audio because I gave a silent lecture this morning in Calculus 2, so I want to do that again. First order of business, let's talk about a little theorem. If we have sequence, right, in normed space, and x sub n converges to x, then the norm of xn is less than or equal to m for all n in n. Let me say that. Then there exists, let me not be in, let me actually put some proper. Then there exists, there exists, m greater than 0 such that the norm of xn is less than or equal to m for all n. In other words, a convergent sequence is a bounded one. So we realized in trying to prove the product of the scalar sequence with the vector sequence theorem last time, we realized that we needed this boundedness in order to set up the estimate that we wanted, right? So let's work this out. Okay, so suppose that I use a different marker. This one's garbage. Oh, it went in, Audric. It went in. It was like a, not it hit the side. What? Let's suppose xn goes to x, and all right, great. Then let epsilon equals to 1. That's greater than 0, and choose, let's say, n in n, for which n greater than or equal to n implies that the norm of xn minus x is less than 1, right? We can do this because it converges. Then what? Right, yeah, then we know that the norm of xn, right, is equal to the norm of xn minus x plus x. I mean, I think you guys will recognize this argument from real analysis where we proved that a convergent sequence is a bounded sequence. It's the same proof, I think. So this is less than or equal to the norm of xn minus x plus the norm of x. But we know that the norm of xn minus x is less than 1, right? So this is less than 1 plus the norm of x. So by golly, call that m, and we're done. So I'm meaning to share with you guys my my Calculus 1 notes. I didn't quite get to it, but I will share with you guys my Calculus 1 notes. If you look in the appendix to there, I have an argument for the product of the limit product rule, and you can kind of follow that to come up with the estimate that you need here. Because what you want to do for that problem we were talking about last time is you need like one of the m's to make the f term small, one of the m's to make the lambda term small, and then in addition to all that, you use like and then you want another m which makes it bounded. So that way you get you pick the max of all three of those things, and it gives you a way to like control that thing we were looking at last time. So this is the extra, that's the other piece we need, is that the sequence is bounded. And of course this is also true for the scalar sequence, right? Like I mean it's also true for real or complex valued sequences. So any questions, Audric? Well, my thought, now, am I wrong? Would you rather be closer and get less?
Yes, I'd rather be moved around.
Okay. You know, I need to put you on a cart.
That would be funny. I would feel like
what am I thinking? What, isn't there something where they're like little people like on the like little robot, like segways with like the monitor that they're coming into every, oh.
I saw it on Big Bang Theory once.
Oh, that's what that's from. Oh, whoa. Let's see where we are now.
Yep.
Okay, so that gets you, what board is that?
The middle board. I can't see the far. I can't see your right on your right side of the board.
So that's middle board.
Yeah.
Okay, let's.
I can only see the middle board.
That should probably be okay then. All right, so definition. Equivalence of norms. All right, so if you have two norms defined on the same vector space, they're called equivalent if they define the same convergence. More precisely, so we say norm 1 is equivalent to norm 2 on E if, you know, xn, good grief, xn minus x, the norm of that goes to 0 in the one norm if and only if the norm of xn minus x with respect to the two norm goes to 0. All right, and that's for any sequence in E and any x in E. So this is equivalence of norms. And he points out that on R2, the Euclidean norm, oh man, that's weirding me out. Okay, so he's called, so his notation, he just numbered them 1, 2, 3 in example 1.310, which is at odds with my numbering last time, but whatever. So those different norms we talked about in R2 are equivalent, all right? Let's talk about why, theorem. So, so norm 1 and norm 2, equivalent, all right, if and only if there exists alpha and beta positive, all right, such that alpha times the norm of x1 is less than or equal to the norm of x2 is less than or equal to beta times the norm of x1. And that's for all x in E. So let's see here, proof. So let's suppose the condition, you know, I mean, suppose star. So I'm calling all of this here star, right? And then, so suppose and the norm of xn minus x with respect to the one norm goes to 0. Then what can we say? We'd like to prove that the norm of xn with respect to x with respect to the two norm is also 0. How do we do it? Given star. That 2 is supposed to be outside. These are outside. I'm a dummy. Those are outside, of course. The whole point here is they're different norms. Dummy. Me, not you. That's here.
beta on both sides, and then we get beta epsilon on the right side, and then we get beta epsilon that's bigger than beta equals 2.
Yeah.
But then at the beginning, we just choose epsilon over beta, then, well, because beta is greater than 0.
Right.
Does that work?
Yeah, I mean, I think we could get down into those kind of details, but I'm trying to stay out of that because I think we can use the squeeze theorem to prove this. So like, look at that. 1 over beta x2 is less than or equal to, right? So we have 0 is less than or equal to 1 over beta norm of x2, xn minus x, right? Is less than or equal to the norm of xn minus x with respect to the 1 norm, right? So therefore, by the squeeze theorem, the sequence 1 over beta times the 2 norm of, 1 over beta xn minus x goes to 0 by squeeze theorem. And then therefore that's what we want, right? We want that it converges in the other norm. And then by symmetry, we can do the other way around, right? Because, well, I guess you could say, well, there's not really symmetry here because that inequality has a different role between 1 and 2, doesn't it?
Yeah,
but
it's still going to 0, so.
Yeah. So, but I think, let's see, I think the other way would be, well, the other way is even easier, right? Because if you're assuming that the 2 norm sequence goes to 0, then you can squeeze immediately by the given.
Yeah.
So basically, this double inequality gives you the ability to squeeze either way. That's the point. So that's I guess, the converse direction of this proof, right? So how do we do the other direction here? Is that okay, Audric? Is that okay?
Yeah, I don't know if it's on my end, but I just sort of, you guys sound soft.
I sound soft? Is that better? Now I'll be deafening in the mic. All right, let me go the other direction here. Oh, what?
Is there a way to go zoom out real quick?
Oh, just a second. I'll get it.
I just realized I was in one corner of the board. I'm sorry. Didn't mean to interrupt.
You're fine. Oh, yeah. I see what you're talking about.
Yeah, thanks. Sorry.
I was just too far zoomed in. Okay, so. So he actually doesn't even prove that in the book, right? He just says that that's clear. And the other direction he does prove, he says, suppose the norm of xn minus x and the 1 norm goes to 0 if and only if the norm of xn minus x and the 2 norm goes to 0, right? For all sequences and points, right? And then he's like, okay, so suppose towards a contradiction that there does not exist alpha greater than 0 such that, and he's just going to pick on alpha times the norm of x1. I keep putting the 1 outside. Alpha, 1 norm of x is less than or equal to 2 norm of x. All right? For every x in E. All right, so what he says is like, then, for each n in the natural numbers, there exists x sub n in E such that n in n, let's see if we can process here. 1 over n norm of x sub n in the 1 norm is greater than the norm of xn in the 2 norm. So if there does not exist an alpha greater than 0, right, that means yeah, so it's the opposite inequality, right? So it's gone from less than or equal to greater than here. I guess if there were no such n, then that would imply that there exists an alpha greater than 0 such that that is holding. I guess that must be the point here, yeah? Then what? It's like, well, let y sub n, 1 over the square root of n, xn over the length, well, the norm of xn in the 2 norm. And what happens to, what happens to the norm of y2? Norm of yn with respect to the 2 norm goes to, you know, well, it's equal to 1 over root n, right? Which goes to 0. So this sequence converges to 0 in the 2 norm. Yeah. But I guess the question is, what happens to it in the 1 norm? Yet the norm of yn in the 1 norm is greater than or equal to n norm of yn in the 2 norm, which, by the way, is greater than or equal to square root of n. This made perfect sense to me when I read it, like yesterday. Now that I'm writing it on the board, I have to get away from it. See here. Oh, yeah. Yeah. Oh, yeah, yeah. Let's see here. So if we take the 1 norm of this, we get 1 over root n xn 1 norm divided by, well, it's still going to be the norm, the 2 norm of xn, right?
Yeah, but then the norm n1 is greater than n times norm of
Oh, then we're using this right here to replace that with what? So this is, yeah, okay, greater than
1 over square root of n times n times the 2 norm is 1. So
yeah. So basically, yeah, the point is we can take this and it gives us the estimate that the 2 norm of xn divided by the 1 norm of xn is smaller than 1 over n. So like, wait a minute. Is that flippity flopped?
No,
Oh, it's fine, it's fine, it's fine. I just... And so that's what we wrote. And so then, okay, well, that's a problem, right? Because obviously then the sequence y sub n does not converge in the one norm because it's above root n, right? So it can't converge to 0, certainly, if it's always larger than the square root of n sequence, which diverges. So, and yet, in the 2 norm, it does converge to 0. So that is a contradiction to the original thing, and so there you go. So this condition here, star condition, is a convenient characterization of when 2 norms are equivalent, right? And of course, the definition of 2 norms being equivalent, meaning that they give the same convergence, is really what you want to think about, right? Like conceptually, that's what you want to hang your hat on. So, are we good? I'm gonna move on here. So this brings us to lemma. So I'll try to stay in this middle board here, Audric, if that works. Is that? Do you want me to get you closer? Well, I can't actually. I got no cord. Okay, so again, I'm sorry, I forgot to find my adapter. Maybe next week I'll get a little bit more electrical cord. I'll put you closer and we'll just be on one board. Maybe. All right, so so lemma. So what we're after right now, guys, is the proof that all norms on a finite dimensional vector space are equivalent. So that's something I've said before, but I've never actually proved it in one of the classes I've taught. So I think it's interesting that we're doing this today. So let's see. So if x1, x2, xn are linearly independent in a normed linear space E, all right, then there exists a constant C greater than 0 such that the norm of alpha 1 x1 plus alpha 2 x2 plus plus alpha n xn is greater than or equal to C times the sum of the absolute values of the scalars. So I suppose we're either working over the reals or the complexes here. Oh, nope, for all, it's reals. It's reals for all alpha 1, alpha 2, alpha n in the reals. All right, so this is the lemma. Let's see how to prove it. So this is equation 1.8 in the text, all right? He says, since 1.8 holds for any C, if, well, okay, so like special case, if the norm, absolute value of the constants, right, adds to 0, then true, right? Then we're done. Because of course 0 is less than, and you do C times 0, you pick C equal to 1, right? We're fine. So what's more interesting, of course, is the case that the sum of the absolute values of the constants, so we're going to suppose that the sum of the absolute values of the constants is greater than 0. And he points out that if that's the case, then 1.8 is equivalent. We can look at it as just the norm of beta 1x1 plus plus beta n xn greater than or equal to c whenever the sum of the sum of the absolute values of the constants here works out to 1. So he's saying that that equation, 1.8, and this equation, well, this pair of equations, right, really, are equivalent. Does that make sense? So if that's positive, like if this is positive, we can take equation 1.8, right, and we can divide by that constant. And when we do that, we're going to get alpha 1 over that sum, right? So like, if you divide by the constant directly, if you just think about it, it's going to give you like alpha 1 over the sum, you know, x1. And then alpha 2 over the same sum, x2, and so forth. Alpha n over the sum, xn, right? And then we're calling those, we're relabeling those beta 1, beta 2, beta 3. Now if you just called those arbitrary beta, that wouldn't be fair, right? Because those betas are, they're constructed in such a way that there's a relation going on here, right? Because like when you look at the you know, the absolute value of alpha j over the sum, what do you get? Well, you get the absolute value of alpha j over the sum, right? Because that sum is positive, it pulls out. So when you add up the sums of the absolute values of the betas, you're going to get a sum of the absolute values of the alphas divided by, there's that common division by sum, so then you get sum over sum, which is then 1, which is why we need to assume this, because if these coefficients are constructed by dividing, they have to be such that the sum of the absolute values is 1. It's just that. So it's a sneaky trick, but there it is. All right. I mean, obviously, this is an easier thing to think about than that, right? What's next? Ooh, well, fancy pants. Look at this. He says, let f from Rn to R, all right, be defined by f of beta 1, beta 2, beta n equal to norm of beta 1 x1, beta 2 x2, beta n xn. I'm sure glad there's only one norm going on right now. It's nice. Now, he argues that this is a continuous function. Yeah? I would point out that the reason that this is a continuous function on Rn is because it's the composition of a sum of scalar multiples. Those are continuous. Like the process of adding and multiplying in Rn, those are continuous operations. And taking the norm is also continuous in the sense of being a function, in terms of being a mapping from Rn to R. Of course, you could just prove continuity, the claimed continuity directly here, and that might be a homework problem, in fact, right? You know, for each epsilon greater than 0, can you show that the value of the function minus, you know, anyway, you could try to prove continuity directly, and okay, let me not digress. Anyway, it's clear it's continuous. Let's just agree that. And since if we look at B, the set, which is beta 1, beta n in Rn, such that the absolute value of beta 1 plus the absolute value of beta 2, absolute value of beta n equal to 1. Well, what is that? He points out that that is a closed and bounded set. So I'm not sure that's entirely obvious. If it depends on your experience. So like, for example, if you have this is beta 1 and this is beta 2, and we're in 2 dimensions, if you look at the solution set of, say, norm of absolute value beta 1 plus absolute value beta 2 equals to 1. So like in quadrant 1, that's literally beta 1 plus beta 2 equal to 1, also known as beta 2 is 1 minus beta 1, which gives you this. So that's 1, quadrant 1. In quadrant 2, you've got, the norm of beta 1 is minus beta 1. Excuse me, the absolute value of beta 1 is minus beta 1. The absolute value of beta 2 in quadrant 2 is beta 2 again. So what's that give you? That gives you beta 2 is equal to 1 plus beta 1, which is this graph. And you can sort through the other quadrants. What you get is a diamond. So, oh, that's right. Just because I shouldn't conflate the webcam with the the video. So yeah, it's a diamond. And so that's closed. It's closed because it's curves are closed, all right, in R2. And generically speaking, as just kind of a generic comment, if something's defined by an equation, you can prove it's closed. And so I'm sure that comment could be taken out of context and be wrong, but and this is bounded, right? Because you can fit it inside a ball of sufficiently large radius. Now, what does this get us? All right, so it's closed, it's bounded, it's continuous. So thus, F attains minimum on B, right? And it can't be 0. Why can't it be 0? But if F was 0, what would that mean? Yeah, that if F was 0, yeah. Right, that would make this equal to 0, which would contradict our assumption that this is greater than or equal to C. Well, hold on a second. Well, we're trying to prove that though, right? So we can't use that. That would be easy, right? What would it mean? Well, okay, so you're not wrong, Audric, but you're probably saying the same. So the point is that would not 0 since if we have the norm of beta 1 x1 plus da 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 plus beta n xn equals to 0, that implies that beta 1 x1 plus beta n xn is equal to 0 without the norm, right? Because the only vector that has 0 norm is the 0 vector. But that being 0 forces what? Exactly, that forces the coefficients to be 0. Why? Exactly, because we're always in the backdrop of we've assumed that x1 through xn is a linearly independent set. So, and that's a contradiction to the linear independence of x1 through xn. Sorry, my handwriting gets...
It implies that betas are all zero.
Right, because remember, well, excuse me, the contradiction isn't the linear independence of xn, the contradiction is that the sum of the betas is 1, right? I mean,
So it can't be zero. That's this argument. It can't be
so this linear independence is how I'm getting from here to here. From this line to that line is linear independence. The contradiction is that the sum of the betas is supposed to be 1. The sum of the absolute values of the betas is supposed to be 1. If they're all 0, oops. All right, so what then? Okay, so then he says, well, just let C then equal the minimum over, let's say, beta 1. I should have started calling it beta vector if I was smarter. Beta 1 through beta n in B of the values of f taken over that. And what is, well, and you can see what that is. That's the minimum of, I'm going to use it now, beta vector, element of B, haha, it's not too late. Beta 1 x1, beta n xn, right, which is greater than 0. And that proves the theorem. That proves the lemma, is what it proves. Are we good? All right, so let me move on here. Can I erase? Yeah. Okay. So theorem, if E is finite dimensional, then any two norms are equivalent. And this is theorem 1.3.13 in, Introduction to Hilbert Spaces with Applications by Loknith Debnath and Peter Mikuninski. I'm mispronouncing all these names. Sorry. We do like your book. Let's see your proof. All right, so he's like, let E be a finite dimensional vector space and E1 through E on a basis. So suppose E is the span, and we'll take it to be a real span of E1 through En. These are not meant to be the column vectors. These are just an abstract basis, okay? He says, we'll prove that an arbitrary norm in E is equivalent to the 0 norm. Okay, so let the 0 norm be defined by so the basic structure of the proof here is to just take, construct a norm using the fact that you have a basis, all right? So anytime you have a basis, you can just define a norm that makes the basis length 1. And the way to do that is very silly. You just take the absolute values of the sums of the coefficients of the basis. that defines a norm. So you can do this in Rn just the same if you want, but it's not going to match up. Like the distance between points isn't going to make any kind of sense if you compare it to like Euclidean distance. But it's something you can do logically anyway. So that defines the 0 norm. And you can prove that that's a norm. Okay, I won't do that. but we can check that that's indeed a norm. And okay, so then let norm without the 0 be any other norm on E, right? And he says we're going to use, we use theorem 1.3. I think where I'm confused is I said it was a lemma. Oh no. Oh, it's the thing we did earlier. My bad. The equivalence of norms between the star condition and the basic definition. So the thing I started class today, we use that first, which is to say that the norm of alpha 1 E1 plus da 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 plus alpha n En, that is less than or equal to, I mean, this isn't even, this is just properties of norms to start with. This is like triangle inequality and either A or B, I forget which, you know, but we're using the triangle inequality and then we're pulling out the absolute value of the scalars as is our right? And then oh, okay, I'm sorry, I'm an idiot. So what he's saying is we're going to use the theorem I did at the start of class to prove the equivalence of the norms. We're going to show that there's an estimate like I called star. That's the goal at the moment. What's not at all clear to me is how we're going to need to use the technical lemma we did just a second ago to do that, right? We'll see how though. So that's just triangle inequality. What's next? He says that's less than or equal to the maximum of the norm of E1, comma, dot, 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 comma, the norm of En, all right, times the absolute value of alpha 1 plus dot, 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 plus the absolute value of alpha n. Right? But if this is a basis, right, that means that we've taken an arbitrary linear combination, you know, of a basis, of an element, and we've, I mean, this is, he says that thus, therefore, for any, he says this implies then that the norm of x is less than or equal to beta times the 0 norm of x. What's the beta? Where beta is the max of what? Of these guys. The lengths of the vector basis with respect to the norm. That makes sense, right? Because I mean, it's literally what's written right there, right? So this is x. If this is x, right? Then this, by definition, over here is the norm, the 0 norm of x. And so this is just that. And what else? And he says, okay, then likewise, there exists alpha greater than 0 such that alpha times the 0 norm of x is less than or equal to the norm of x for all x in E by the lemma. By the lemma. Does that make sense? I wish I hadn't erased the lemma. Oh well. Let me look at it for myself here. So the lemma, oh yeah, I mean the lemma, if you look back at it, it is literally the norm of x is greater than or equal to c times the 0 norm of x. Like in terms of our current notation, that is just manifestly the case from the lemma. Yeah, so we have alpha norm of x naught less than or equal to norm of x, which was an arbitrary norm, less than or equal to beta times the norm of x naught. The naught's on the outside, my bad. So therefore, norm is equivalent to 0 norm. But since the norm was arbitrary, we've proved that any two norms on a finite dimensional vector space are in fact equivalent. That actually wasn't that hard. That's really cool. Why haven't I been doing this proof already? I think it's because I had other things to teach in those classes, yeah? But maybe I should have been. I think this is one of my new favorite proofs. Cool. Okay, so what's up next? Any questions, Audric, or?
No, I'm following that. I have to look back to the book that I read that recently.
Oh, I'm sorry.
But it's pretty good. No, that's good.
So let's talk about the induced metric. So given E with a norm can define a distance function from E cross E into the reals, right, by the distance from x to y is equal to the norm of x. Well, I guess I don't remember y minus x, x minus y. It doesn't really matter, right? Because, of course, by properties of the norm, that's equal to x minus y, right? Which would be then for us the distance y to x. So this distance function is symmetric, right? And what else do we have? The distance function from x to x is norm of x minus x, which is equal to norm of 0, which is 0. And that's true if and only if, right? Like, think about this. It's more than just that, right? The distance from x comma y is not equal to 0 for x not equal to y. Because in order to have distance 0, you'd have the norm of x minus y as 0, which then forces x minus y to be 0, which means x is equal to y. So we have that. And also, if we look at the distance from, say, x comma y plus the distance from y comma z, that's equal to, I'm kind of doing this backwards, but you'll forgive me, x minus y plus the norm of, y minus z. I'm probably not being consistent with my choice of subtraction, my bad. But then by the triangle inequality, what's that? This is greater than or equal to the norm of what? X minus y plus y minus z, which is equal to the norm of x minus z, which is equal to the distance from x to z, right? So the triangle inequality for the norm implies the corresponding triangle inequality for the distance function induced from the norm. So if you have a space, right, and you pair it with a distance function, this is called a metric space. So metric space is a definition, a set S paired with a distance function is metric space. And that distance function has to be symmetric, and it has to be such that it's only equal to 0 if you put the same, the distance from any point to itself is 0, but the distance between any two other points that are distinct can't be 0. And it satisfies the triangle inequality, right? This is a metric space. And once you define that, you can talk about epsilon balls, right? Like the epsilon ball centered at x naught would be like x in the space such that what? Such that the distance from x to x naught is less than epsilon, right? So this is the epsilon ball. Yeah, and then he talks about the closed epsilon ball, right? Is what? Less than or equal to epsilon. And then he talks about the sphere. This is not his notation. My bad. What's his notation? He's got his own groovy notation. Oh, he does. He just does. So he puts the b of x naught comma epsilon like that, and b of x naught comma epsilon with a bar over it like that, and then sphere x naught comma epsilon like this for the boundary. I know we don't know what boundary is yet in here, or well, you'll learn in topology soon enough. The boundary is the edge of things, right? I mean, but that's just the equality. So sphere, so open ball, closed ball, sphere. Radius epsilon centered at x naught, each one, all right? And so, I always draw a picture in this kind of discussion about the different open balls in R2 with respect to the different norms. So like in R2, we can talk about, let's talk about this. We usually call the sphere a circle in R2, right? So like the circle centered at the origin of radius 1. So this would be basically the unit circle in our usual language. And so the unit circle from different norms is different, right? So of course the unit circle is literally the circle for the 2 norm, but for the 1 norm we go back to that diamond I just erased. Although the 1 norm apparently is we've been calling it the 0 one for today in some sense, but not exactly. That's a more abstract construction, so I don't feel too bad about it. But so let me see here. So what we're looking at here essentially is x. Well, I guess say x comma y, 2 norm equals to 1 is the unit circle. In my notation, right? X comma y. 1 norm, which is, I said, norm of absolute value of x plus absolute value equal to 1. That's your diamond. And then at the far extreme of everything else, of course, you can talk about the 3 norm and the 4 norm and all those sort of truncated LP norms. I think of them that way. You eventually get to the sup norm, or sub. So the infinity norm, which is the max of the absolute value of x and y. And if you look at that equal to 1, sorry, I'm on the edge of things. If you look at that equal to 1, well, that gives you this. So the circle, with respect to the sup norm, literally is a square. Now, philosophers, since I don't know, a couple hundred years of being, you can't square the circle. You can't imagine squaring the circle. Yes, I can. It's right here. All day long. You guys just need to get with the math of like 150 years ago. Uh-oh. Aw, man. Well, he'll be late to the appointment. Just a second here. So, so that's just a little bit. Let me just say just a little bit more here. So, once we have, if we have a norm, we can define a metric. Then we can define open ball, right? We define an open set to be a set where any point in that set you can find an open ball around the point which is contained in this set, right? So the set of all such points is called the interior of a set. If a set is equal to its interior, it's open. A set is said to be closed if the complement of the set is open, right? Now these are the topological definitions of open and closed. There's also sequential definitions of open and at least of closed, which we'll talk more about like in the next class or something, right? Now there's a larger question here, which is more difficult to answer but interesting, which is, given a metric space, when is it actually the case that that metric can be induced from a norm? So first of all, if the metric space is not a vector space, well, game over. That's an easy part, right? But so suppose you've got a vector space with a metric, right? When is that a normed linear space? And there, the answer is more complicated. There exist metrics. There exist vector spaces that have a metric, yet it can't be written in terms of a norm. I think really that, but I'm getting ahead of the story here, because really what I really want to say is that there exist no, I think I'm saying this wrong. I'm thinking about the interplay between inner products and norms. I feel like I'm messing this up. Oh, anyway, I got to go to my meeting, so let's I'll bail. Sorry, I hate to leave the lecture on a note like that, but what it is, it is. So thanks, guys.